To complete our introduction, I want to go ahead and talk a little bit about directional fields. And what directional fields are, they're a good tool to be able to understand some qualitative properties about your particular types of ODEs. So let's assume that we have an ODE of a specific form, y prime equals f of x comma y. Now remember, normally, or let's say more generally, our ODE is going to be of the form y to the, with n derivatives equals f of x, y, y prime, and so on and so forth. But directional fields will not work in the form that we're going to discuss them for this type of problem, only for y prime equals f of x comma y. And the basic idea of a directional field is if you have an ODE of the form y prime equals f of x comma y, well, what that is telling you graphically is that the slope of y is equal to this function. So let's take a concrete example. Let's say y prime equals x times y. Well, that means that just hypothetically, the slope of y at the point, let's say 4, 3 is, well, if you're at the point x is 4, y is 3, then the slope of y, that's y prime, is going to be 4 times 3, which is 12. And of course, you can take any point, x comma y, and you can figure out what the slope of y is going to be at that particular point. So what you can do with this information is you can construct what we are calling a directional field. And essentially what that means is you can take as many points as you'd like, and you can illustrate what the slope of the tangent line is going to be. So at 4, 3, if I put this on a graph, 4, 3, the slope is going to be 12, which is going to be pretty steep, right? I'm not going to do this exactly, but it's going to be fairly steep. Whereas if you wanted to know the slope of the tangent line to y at 1, 1, well, 1 times 1 would be 1. It's not going to be as steep. Let me go ahead and do this in yellow so that it's a little clearer. So very steep, not as steep. And in fact, we can get some nice information. The slope of the tangent line at whenever x is 0 and y is 0 is going to be 0. All right, so you can't see this very well, but I'm just drawing little horizontal lines because if the slope of the tangent line is 0, then that means you have a horizontal tangent line. And so at all x equals 0 and y equals 0, the slope of the tangent line is 0. If you go to 1, 2, the slope is going to be 2 because, well, 1 times 2 is 2, so it's going to be steeper here. It's going to be steeper here. And you can see that I'm starting to fill in what the slope of the tangent line should be. And you're also probably starting to realize that this is a very inexact thing when done by hand. The best way to construct these is using some sort of computer tool, but you can get the idea of what's going on with the solution by constructing at least a basic version by hand. So if I go to the negative x coordinates here, then I see that, let's see, negative 1 times 1, I would have a slope of a tangent line of negative 1 at negative 1 comma positive 1. If I go to negative 1 comma positive 2, negative 1 times 2 is, well, negative 2, so it's going to be a little bit steeper. And so I can kind of at least get a sense of what the solution is doing because these are the lines that the solution has to be perpendicular to. So, perpendicular to, how ridiculous. The solution has to be tangent to. So if you pin down that, let's say this point right here, 1, 1, is on your solution, then, well, your solution is going to have to be tangent to this directional field line that I've drawn, and it's going to have to look something like this. Why did I draw it going up? Well, it seems to me that these tangent lines are very steep. They're getting steeper. What's going to happen over as the solution goes to the left? Well, it's probably going to level out and then go something like this. And that is supposing that you have the point 1, 1 on your graph. Now, this goes back to something that we talked about earlier. If you just specify the ordinary differential equation, you're going to have infinitely many solutions. And now with this directional field, you'll get infinitely many solutions based on where you put one point on the graph of your solution. If you put a point, let's do this light blue here. If you put a point here, if you say that's a point on my solution curve, well then I can see that my solution is just going to be 0 because all these tangent lines are 0. More accurately, you would start at the point that is on your graph and you'd say, okay, this tangent line has to be 0, and all the other tangent lines, if you go in this direction, have slope 0, so that's going to give me what's called the 0 solution, the solution which is 0. So this directional field will give you a sense of what's going on with your solution. Then when you pin down exactly one point, what we've called sort of the initial condition, then you can say, you can draw a sketch of your curve and at least get the basic idea of what's going on with your solution. So for example, for this particular ODE, it looks like if I have the initial condition 0, 2, that is x equals 0, y equals 2, which would likely be stated as y of 0 equals 2 in an initial value problem. Well, it looks like if you go, as the x goes forward, it looks like my solution is going to skyrocket based on these slopes of these tangent lines. Okay, so again, it only works with if you have y prime equals to some function of x and y, but if you do have an equation of that form, then you can construct these directional fields just by selecting some x and y coordinates, figuring out what the slope of your solution should be, and then drawing in those slopes on an xy plane. And of course, you can't draw all of them, and it's a very subjective thing how many you need to draw. And the reality is that you need to understand how to draw it so that you can understand what's going on when you use a computer tool in order to draw these directional fields. These are never drawn by hand, but you need to know how to draw them by hand because you need to know what the computer is doing. Let me go ahead and show you a computer tool that you can use on the web in order to draw these. Okay, so this is Geogebra.org, and it is a directional field plotter within Geogebra. And how it works is you just put in what your, this labels it as f prime here, but this is our y prime. And you just put what it is. So I put x times y, you put your max and min x coordinates, your max and min y coordinates, and density, I believe, is how many of these tangent lines that you want to draw and what you want the length of them to be. Let's see, so if we increase this, then we see more tangent lines here. And if we increase the length, then those tangent lines will be shown as longer. And you see a very similar thing, well, similar to what I've drawn in the sense that, they match similar behaviors. This is obviously much nicer. And now if you go ahead and specify an initial condition, I'm going to go ahead and select this solution A here. It will show you what the solution is that corresponds to that initial condition, or at least it'll show you a sketch of it. So if I go ahead and drag this here to 1, 1, then you'll see something similar to what I've drawn. If you drag it to 1, 0, you see you get this 0 solution here. And so you can go ahead and play around with different initial conditions and see what happens to the solution. So it's a very useful tool. For example, imagine that we had our population model, and I guess we don't even have to imagine it, right? Let's go ahead and do 2 times y. So this should be our, if we didn't know anything about our population model, if we hadn't discussed it yet, we could go ahead and create a directional field, and we could go ahead and see what's going on with our solution. So we see here that we're getting exponential curves. And then if we hadn't done the analysis of what the solution is to the exponential model, y prime equals 2 times y, then we could get some sort of idea, at least, of what our ODE does. And that can be critically important in problems in practice. Sometimes, ODEs, they tend to be very challenging. We're going to talk about some very basic techniques, but they tend to be challenging to solve. And so if you can get some sort of picture which describes what happens with your ODE, then a lot of times that can assist you in whatever application you're working on. So this can be a very, very useful tool. However, I'm not going to expect you to be able to construct such a beautiful picture here. What I will expect you to be able to do is, if I said, here is an ODE, y prime equals x times y, and I said what would be the slope on the directional field that you put at 1, 1, I would expect you to be able to answer that question. So essentially you need to know how this is constructed, but you don't need to construct such a beautiful one yourself with all of these curves drawn.